This is the second lecture in the free radicals. When I looked at the problems, actually, that I said you should be able to do, you're not going to be able to do until this, after this lecture, right? So, in order to answer those questions, we have to talk about whether or not all free radicals that we talked about, are they all same in reactivity and stability, or are they different? And as you might have imagined, depending on what free radical you're looking at, the reactivity and the stability is different. So like the stability trend of the carbocation, sort of similar to that, the stability of radicals are not identical. So let's take a look at the different radicals that you might encounter, okay, and compare. So halogen radicals are commonly seen. So let's look at chlorine radical versus bromine radical. So are they different in reactivity? Yes. And which one do you think might be more stable when you compare chlorine versus bromine? And remember, the free radicals are electron deficient, so it wants electrons desperately. So which of these two, chlorine versus bromine, is more electronegative? You should know, looking at the periodic table, that the chlorine is more electronegative. Right? So what does that mean? Chlorine is a lot less happier being a radical than bromine is. So that means that because chlorine is a lot less happy not having the full electrons, is going to be more reactive. Than bromine. So in other words, bromine is more stable. So we could actually see this in a reaction where we take this compound, isopropane, and react with the chlorine radical, and you will find that you have a mixture of products. This is about 70% and this is about 30%. Whereas if I react the same starting material and react with the bromine radical, I only get one product. All right. So this is illustrating that the chlorine radical, because it's so reactive, it's basically reacting with any hydrogen that it encounters. So there's only one hydrogen here that it could abstract, or there's 3 hydrogens in each of these methyl groups. All right. So the chlorine radical is reacting at both sites, whereas bromine radical is a lot more selective in that it only reacts at that carbon with that one hydrogen. And when we look at the stability of the carbon radicals, you'll understand why this is the case. All right, so think of chlorine radical, because it's so much more more reactive than the bromine radical, as being not choosy, like very some of the scientists describe these very reactive radicals as being promiscuous. In other words, it just goes and reacts with any substituent there is, whereas bromine radical is, because it's not as reactive, it's a lot more selective, and it will only react at a place where it makes sense, if you will, when we talk about the stability of carbon radicals. All right, so just keep that in mind in the reactivity. All right, another radical that we're going to look at is a hydroxy radical versus phenoxy radical. So in here we're not comparing two different atoms in terms of radical reactivity, but they're both oxygen radicals, as you can see. One is a hydroxy radical, and the other one is the oxygen radical as well, but it's connected to a benzene ring. All right. So when you compare these two, then what you are looking at is what is the difference between having a hydrogen versus the benzene ring on the oxygen. And okay, so think about the fact that both oxygens are electrophilic, and what would be more stabilizing component to the oxygen radical. As you might have guessed, through resonance, this is the stabilizing factor, right? So it's stabilizing the oxygen radical via resonance. And you could draw the resonance by, you know, having a radical here, for example. If you put this radical here and then take one of the two electrons of the double bond and make the double bond here. Okay, so let's draw the single-headed arrows. So then you could see that you have a radical here. So by being able to draw these resonance structures means that the benzene ring is contributing in stabilizing this phenoxy radical, whereas here you cannot draw any resonance. So this is going to be like chlorine in that it's going to be more reactive. It's not as stable as the phenoxy radical, right? So once again, this is going to be very promiscuous in reacting with any substrates, whereas the phenoxy radical is going to be more selective, more stabilized. All right. Now let's look at the carbon radicals, and here you should see the same trend that you saw as the carbocation stability. All right. So you see that the methyl radical, which has no inductive effect because the hydrogens are very small in electron density, is going to be the least stable, followed by primary. So if you have some R group, it's going to be able to inductively stabilize that carbon. And if you have two R group, that's going to be even better. And then tertiary free radical carbons are going to be even more stable. So in this reaction that we just briefly went over, the bromine is able to abstract this proton in creating a carbon radical at the tertiary center, which is the intermediate that reacts with the bromine to form this. All right, so I'll go over the mechanism of free radical reaction, but notice that bromine is because it's selective, it allows you to form the more stable tertiary radical in this case, whereas chlorine, because it's so reactive, is forming not only the tertiary radical but also the primary radical. All right, so compared to the tertiary radical, even more stable than that, so on right side of the tertiary radical would be the allyl radicals and benzylic. Radicals. So these are more stable than the tertiary, and the reason for that is due to resonance. Just like you saw over here for the phenoxy, same argument goes with the allyl radical, where you could draw a resonance. So that means these pi electrons are contributing in stabilizing the radical. So these are going to be more stable than regular alkyl radicals due to resonance. All right. So in fact, the very first free radical that was isolated back in the 1900s was a free radical that was stabilized by 3 phenyl groups, and this this radical was isolated in the 1900 because it was not short-lived. Scientists were actually able to isolate it because it was so stable. All right, so you should now be able to do those problems, which basically asks about the stability of these radicals, and be able to do problems in which you're comparing and contrasting, and then asking you the reasons why one radical is more stable than the other. All right. So the next topic that I want to go over is the how radicals react. I mean, what is the mechanism of free radical reactions? All right. So to illustrate this, I'm going to be using a reaction in which, very simple reaction, in which methane reacts with the chlorine with the help of UV light, and is showing the mechanism that we're about to see is showing how chloromethane will be formed. But in this reaction, because chlorine is so reactive, it forms mixture of compounds, and some of the mixture will be methylene chloride, chloroform. It could make ethane. So there's mixture of products that are forming, and the mechanism that is showing is how this product is going to be forming. All right. So unlike regular reaction mechanism, free radical mechanism goes through 3 stages. So the 3 stages are, is written here, the initiation stage, and then the propagation stage. So this is 1, this is 2, and then the next page will have the last stage, which is a termination stage. All right. So it's a bit more complicated than reactions that you've seen, but we'll go through them and then see how some of these products may have formed. All right. So rather than dive into this, I'm going to stop here because I only got a minute left, and then I'll go over in the next lecture.